We talked about kinetic theory a little bit. Now we need to connect that to gases. So we saw that in um, solids, you have a kind of spring lattice amongst the molecules. And then in a liquid, those molecules start to break that lattice and slide by each other. And in a gas, they start to fly away completely. And that we can talk about what happens in that process with what's called the ideal gas law. So let's go back to kinetics here. So we go back to our container that we remember if you it started with ice in a closed container with a vacuum above it. We added some heat. Those molecules started sliding past each other and became a fluid. And we add a little more heat, and the molecules actually start to escape the attractions they have with each other. And the molecules fly out into that vacuum as a water vapor, as a gas. Now, they're flying around this container. Remember, they're moving in random directions. They're moving really quickly with high velocities. And they start banging into each other and into the walls of the canister. Every time it bangs into the wall of the canister, what happens? Well, you have a collision. And we know in a collision, you get an exchange of momentum. And that exchange of momentum, it works as a force here, right? What is an impulse? It's a force times a time. And so you get those molecules banging into the side of the container. And when you have billions of them inside this container doing that, it adds up to a significant force. And that is called pressure. That's what pressure is. It's just these molecules banging against a surface. We can measure pressure in force per area. And so that would be something like newtons per meter squared in the metric system, which we call pascals. So what does that mean, force per area? Well, it means that if you have a given pressure in a container, then the amount of force that it's going to create has to do with the surface area of that container. Because we're talking about collisions with that container, the more area we have, the more opportunity we have for collisions. As the vapor gets hotter, the kinetic energy of the molecules grows, right? They start to move faster. That's what temperature is. Okay, they bang into the walls more often and with more momentum. So when we have more momentum exchange, we have larger impulse, and that means we have larger forces. And so that increases the pressure within the container. So as we add energy here, we're going to increase the pressure in that container. And this is why you may have noticed this recently. Your tire pressure went down, right? In your car once it got cold. That's because those air molecules, it's not because they're leaving the tire, it's because they're moving less quickly. And if we heated that gas up again, the tire pressure in your tire would go back up. Now, pressure doesn't act on its own. We can think about volume too. And so in this case, we're going to have our container with its water vapor molecules flying around, but we're going to keep the temperature the same. And we're going to shrink the container. Okay, so the molecules have the same velocity, but as we've shrunk the container, they're going to hit the walls more often because the walls are close together. There's not a lot of space for them to move around, and so they're going to bang into the walls more often, and that increases the pressure too. So even if we keep the temperature the same, if we shrink the amount of volume that those molecules can move around in, then we're going to increase the pressure of the gas. We can think of this as a resistance to compression. If you think of our canister as having a piston in it, if it's at a certain temperature and a certain pressure, and I press down on that piston, right? That material doesn't want to be compressed anymore. It was kind of happy in the medium, in a balance that it had between the pressure of the piston on it and the pressure that the gas was creating. So I press down on it, and it wants to expand back into a larger volume. And so it starts banging on the top of that piston a lot. So we can think of pressure as a resistance to compression, almost as if it were a spring. We can think of those molecules, to push them together is like pushing a spring together, and it wants to expand out again. So at a molecular level, we can think of pressure in a gas as molecules bombarding a surface. Pressure happens because intermolecular repulsive forces resist the attempt to move molecules close together. That's that spring, right? If we push those molecules together, they don't really want to be together, and so they're going to push back. When it's compressed, it's going to try and spring back. And we can even think of that pressure as being stored energy, right? If I think about that piston and I push down on that piston, what's going to happen when I let go of the push piston? It's going to push back up, right? It's going to create some velocity in that piston, and so it's almost it is a stored energy. It's a potential energy that can create movement in that piston. So we can pull all these together and come back to what's called the ideal gas law, which I imagine you've run into in your chemistry classes. But let's imagine we have a set mass of an ideal gas in a container. And what's an ideal gas? It's a small molecule gas that is in a situation where the size of the molecule doesn't really affect how the molecules are interacting. If we compress molecules really tightly, then at some point the size of that molecule starts to matter. We can't just think of it as a point in space. But in most normal Newtonian conditions, we can think of a smaller molecule gas as being an ideal gas. So we're going to change volume, pressure, or temperature, or keep one of those constant as we change something else. So if the volume is increased, will pressure or increase or decrease? And that is, if temperature stays the same and we increase the volume, what happens? Temperature says those molecules are moving at the same pace, right? At the same speed. And what happens is as you increase that volume, the pressure is going to go down, okay? Because there's more room for those molecules to move around. And this results in what's called Boyle's law. The pressure times volume is constant as long as temperature stays the same. If we increase the temperature, what will happen to pressure while we keep volume the same? Well, this is where we speed up those molecules, right? And they're going to bang into the side with more force. That's going to increase our pressure. So temperature and pressure are both going to increase together here if volume stays the same. And so we can write that pressure is equal to some constant times temperature. Now, pressure and temperature have to be absolute here. So if there's zero pressure, we have to have a value of 0. If there's no kinetic energy in the molecules, then temperature has to be 0. So we have to use the Kelvin scale. Finally, if temperature is increased and pressure stays the same, what happens to volume? Well, if we increase our temperature, right, and they start banging on the sides of the wall, our pressure would normally go up, right? So we have to relieve that by making our volume larger. We have to give those faster moving molecules more room to move around in order to keep the pressure the same. And here we can see that our red molecule here is moving more quickly, but we can create the same number of collisions with the surface if we make that volume larger. And that is called Charles' law, where V is equal to a constant times T. So volume and temperature go up together. Now, if we combine all of these together, we get this, okay? And with some kind of constant in here. Now, what's that constant? Well, we can define that by doing some experiments. But we know that these things work together, and that constant ends up to be this very, the common NR, right? Where N is the number of molecules and R is the Boltzmann constant. So this is just a number that makes experiments work, but it works with all sorts of different ideal gases. And it's the interrelations of PV and T that the ideal gas is all about. There are two main assumptions. This last slide is sort of advanced ideal gas law. I'd say at the end of this slide, this does show up on AAMC's list of topics for the MCAT, so I want to include it. And it's interesting. So the assumptions that we made for the ideal gas law are that intermolecular forces don't affect the behavior of gases. In other words, the gases are so far apart and so small that their interactions don't matter, and that the volume of the molecules don't matter. The molecules are so small compared to the volume that we can think of them as point masses. Those are pretty solid assumptions in what we would think of as normal everyday conditions. If our pressure goes way up, right, or our temperature goes way up, then we might have to start thinking about those assumptions. And we can make some adjustments to the ideal gas law. And you can see that this is just the ideal gas law. It's P plus something times V minus something equals nRT. And these have to do with if N gets really big, that is the number of molecules in a particular volume, okay, gets really big, then these numbers start to matter. Most of the time, these are zero in an ideal gas law, or very close to zero. But once we sort of put them under a great amount of pressure and stick a whole bunch of molecules in a relatively small volume, then we can start to see the effects of the van der Waals equation, which is what this guy is. And just a note that this isn't something that'll be on the exam, but it's good to know that the ideal gas law has limits, right? We can't always use it once we get in unusual situations.